Thrusting space science into the audio dimension. This is Naked Astronomy.
Hello, welcome to the fourth of this week's special episodes of Naked Astronomy, brought to you from the National Astronomy Meeting, organised by the Royal Astronomical Society in St Andrews. I'm Dominic Ford, and in today's podcast, what large surveys of the sky are telling us about dark matter. We catch up with some of the more controversial ideas here at NAM, and why avalanches might be a problem for spacecraft landing on asteroids. As always, if you'd like to get in touch, you can tweet at Naked Scientists or drop us an email to astronomy@thenakedscientist.com.
Supported by the STFC, this is Naked Astronomy. For more information, look us up online at nakedscientist.com/astronomy.
Dark matter makes up more than 80% of the material in the universe, and yet we know very little about what it is. It doesn't produce any light of its own, and light produced by other objects can pass freely through it, making it completely invisible to telescopes. Yet it has proven quite impossible to build models of how the universe behaves on the larger scales without it. So what is the evidence that makes it such a necessary part of cosmology? Catherine Haymans from the University of Edinburgh gave a plenary talk earlier in the week.
So there's a whole realm of evidence now. We had another plenary yesterday showing the results from the Planck satellite, and that shows with very high significance a model for our universe that requires a quarter of our universe to be made up of dark matter. But I'll give you an example of a more immediate piece of evidence of dark matter. So let's think about our own Milky Way galaxy. So we've got stars that are spinning round in our own Milky Way galaxy, and you can look how fast they're moving round, and you can do this in lots of galaxies as well. Now, if you imagine a piece of string and a ball on the end of a piece of string, you can swing that ball around. Now, the faster you swing that ball around, the tighter you've got to hold onto the string. Okay, what does this mean for our galaxy? Well, the ball is now your stars, and there's no string that's holding the stars as they go round our galaxy. It's gravity. Now, gravity, you get lots of gravity if you've got lots of mass. And we can see how fast the stars are moving round. We can roughly count how many stars there are in a galaxy. We know roughly how much a star weighs. And there just simply isn't enough gravity in our galaxy to keep those stars going round. They're just moving too fast. And so that means there must be extra mass there, which we call dark matter, to keep those stars going round. If there wasn't a big halo of dark matter around our own Milky Way galaxy, all the stars would just simply fly out into the universe.
Now, I know you're using a technique called weak gravitational lensing to probe dark matter. How does that work?
Einstein had a wonderful theory of general relativity that told us that mass bends space and time. Now, what that means is that if we look at light from the very distant universe, as it comes towards us on Earth, it doesn't travel in straight lines. It gets bent by the gravitational potential of the matter. So we've got lots of dark matter in between us and the distant universe. The light's coming towards us from the distant universe. It gets bent and distorted by the dark matter. And what that does is it leaves an imprint on the images of very distant galaxies. You can imagine it like dark matter just leaving a signature on images of the distant universe. I was here. What it looks like to us on Earth is it looks like the galaxies are kind of lining up with each other. And so that's the signature that we look for. And when we see lots of galaxies all lining up with each other, what we infer is that there's been some dark matter in between us and them that's bent the light to make it look like these galaxies are lining up. And we can use this to tell us where the dark matter is and how much of it there is. And that's the technique that we've used to map out dark matter on very, very large scales in our universe.
So is the idea here that if these galaxies are all lining up in the same orientation, there's got to be either some cosmic conspiracy, which means those galaxies are all in the same orientation, or there's some physics that's making them look that way?
So there is an effect that if you have two galaxies that are really actually physically close to each other in the universe, when they form, they will tend to line up with each other. And we have to account for that as well. But what we do is we look at galaxies that, even though they look like they're close to each other on the sky, they're actually physically very distant. So they're at different distances away from us. And then we know that they can't possibly know about each other, so they can't possibly be lined up with each other. So if we see an alignment, we know it has to have been caused by some intervening dark matter in between us and those galaxies.
So how much uncertainty is there in these models of dark matter? Dark matter's been in cosmology for, must be about 80 years since the work of Fritz Zwicky. Mm-hmm. This must be quite a well-tested theory by now.
It is a very well-tested theory, and there is lots of evidence out there to show that there is dark matter in our universe. Some would say an overwhelming body of evidence supporting this theory of dark matter. The question is now, what on earth is it? So we know that it's weakly interacting, we know that it's cold, but nobody has detected the particle yet. So there have been some exciting new developments in the UK recently, where a new consortium of all of the particle physicists who are involved in this type of research have joined together to support a new project called the Lux Zeppelin detector. So it's going to be 9 tons of xenon deep under the ground, I believe in South Dakota, 5,000 feet underground. And the hope is that one of these weakly interacting matter particles will collide with a nuclei in this big detector. Some electrons will be emitted and they'll be detected. So that's the hope, that we'll actually be able to detect one of these particles, and construction on that project begins next year.
So that's what they call astroparticle physics, where you're looking for the particle which makes up this mass that we can't see, this dark matter.
Exactly. So as astronomers, we work on mapping the dark matter and using simulations of what the dark matter particle might be to predict what our observations should look like. And at the moment, this theory of the cold dark matter particle, the simulations that we have of the universe with that theory match our observations. So now the question is, now we know that we've observed this type of dark matter, can we actually go and detect it? And it's really, really tough, because these particles are very weakly interacting. We detect, as astronomers, we detect it through its gravitational effects. The particle physicists are trying to detect it through an actual reaction, which is really challenging to do.
And I guess on the astronomy side, are you looking to push these weak lensing surveys further? Exactly.
So we've just finished a big project called the Canada, France, Hawaii Telescope Lensing Survey. So you can check it out on www.cfhtlens.org, and you can see all of the exciting results that we've done with that survey, mapping out dark matter on the largest scales ever seen before. And now we're moving on to a new project. It's a European Southern Observatory project called the Killer Degree Survey, or KIDS. And that's going to be 10 times larger than the current project that we've worked on. And that's going to allow us to map out even more dark matter and see how dark matter is affecting the galaxies in our universe. We believe that dark matter dictates where and when the galaxies form, but we want to understand more about that.
And I guess on the more distant horizon, ESA's planning the Euclid spacecraft.
Exactly. So Euclid is going to be absolutely phenomenal when it launches. It's going to survey the whole sky to Hubble Space Telescope-like imaging. So I think everyone's familiar with the fabulous pictures from the Hubble Space Telescope, imagining having that facility across the whole sky. So we're all very excited that Euclid's been selected for launch and that the building has already commenced. So it's due for launch in about 2020.
That was Dr. Catherine Haymans from the University of Edinburgh. Meetings like the National Astronomy Meeting provide an opportunity for the UK's astronomers to exchange ideas and discuss the latest projects and facilities. Sometimes that exchange of ideas can turn into lively debate. In recent decades, the vast majority of cosmologists, like Catherine, have been convinced of the existence of dark matter, but there are still a handful of theorists who have other ideas. As Catherine explained, the key evidence for dark matter on the scale of galaxies is that they spin too fast, as shown on plots that cosmologists call galaxy rotation curves. Dr. Benoît Fabi from the University of Strasbourg sparked controversy this week when he presented results from one of these alternative cosmologies.
So it's called modified Newtonian dynamics, or MOND, and it's not really a theory, it's more a paradigm which is stating that the gravitational field in a galaxy is fundamentally determined by the distribution of baryons in that galaxy. Then there are a few theories of gravity that are designed to reproduce this paradigm, which can explain a lot of phenomenology which we see in galaxies, which is more difficult to explain with the classical dark matter particles paradigm, because this relation between the distribution of visible matter and dark matter in galaxies seems actually to work, at least on galaxy scales. And it's kind of difficult to imagine how dark matter particles can arrange themselves to reproduce very precisely this relation.
So in this paradigm, you don't have any dark matter in your cosmology at all?
Well, it might be a little bit more complicated than that, in the sense that there is a very clear case that something behaving like dissipationless dust fluid must exist on cosmological scales. It could be, in principle, this new theory of gravity. It would, in any case, behave like dark matter on the larger scales and behave purely as a modified gravity theory on galaxy scales.
So would you argue that this is a simpler explanation of how this gravitational glue comes about?
It's actually simpler to explain the phenomenology that we see in galaxies. We can fit almost everything that we see in galaxies with just one free parameter, which would be the mass-to-light ratio, while within the dark matter picture, you need many more free parameters in your dark matter distribution.
Benoit, we'll come back to you in just a moment, but first I want to talk to Hongsheng Zhao from the University of St Andrews, who's applied this to the dynamics of a local group of galaxies. Hongsheng, what have you been doing?
Lately, I've been looking at scales a little bit larger than galaxy scales. Everybody knows that our Milky Way has a neighbor, a big one, called Andromeda. It's about 2 billion light years away from Milky Way. And nobody knows why it is at its present position. And it is also observed to be falling towards Milky Way with a not very big velocity, about 130 kilometers per second.
So people say that the Andromeda Galaxy and the Milky Way might collide in about 5 billion years' time.
Yeah, this problem, we are not the first person to notice this. Back a long time ago, people have noticed if two galaxies so massive and close together, they might gravitationally interact. They're sort of falling towards each other, perhaps as a result of the gravitation. And people have used this argument to say, okay, what if Andromeda was start out fairly close to us and come back to us due to gravitation? And they have used this idea to estimate how much gravitation or how much material you need to generate that gravitation in order to explain its present position and velocity. So Benoit talked about theory of modified gravitation. Fundamentally, that type of theory is based on a kind of observation, which is saying galaxy rotation curves at very large radii is flat. That is a question that interests me. If galaxy rotations do not stop beyond the position of the sun, suppose that kind of a flat rotation curve keeps on going. Suppose Andromeda is actually going inside the same kind of potential, which suppose it was on circular orbit, it will also go flat rotation.
So I think you found that actually, in your model, Andromeda collided with the Milky Way in the past rather than in the future.
Yeah, so that's the surprising thing of it. We say, okay, let's just take this toy model and just integrate it. And in fact, we integrate backwards because we want to know where it was. Surprisingly, the gravitation is fairly strong in this kind of flat rotation curve. And it almost have to predict that it will hit Milky Way somewhere like half of the Hubble time.
So when the universe was about half its current age?
That's right, yeah.
Projects such as the weak lensing surveys that Catherine talked about earlier have produced detailed maps of the distribution of dark matter in the universe. In light of that, many theorists now believe that we know so much about dark matter that there is little useful science that can come out of studying alternative models. Dr. Carol Masters from the University of Portsmouth joined us.
Well, I think it's very important for scientists to explore all different kinds of theories. But as scientists, we have to kind of accept that there can be evidence that disproves our theories. And we also have to, if we're going to change paradigms very significantly, find quite extraordinary evidence. And I think there's an awful lot of extremely good evidence, as Benoit was saying, for lambda CDM, the standard dark matter model, on the very largest scales in the universe. And I think on the smaller scales where proponents of the MOND idea say there's big problems with lambda CDM, I think that there's a lot of physics that we know that we don't understand very well. The physics of star formation, how gas clouds interact. And I think that using evidence on these scales with these types of physics, which we know we don't understand that well and we know can create all sorts of complications, using evidence on those scales to try to throw out our entire theory of gravity is not extraordinary enough evidence to do something that drastic. So I think that just generally, I'm really very well convinced that dark matter is this WIMP, weakly interacting massive particle that people predict it is, and I would be extremely surprised if that's not detected in the next 10 to 20 years. And if it is not detected, the very natural predictions for a WIMP that is missing, that we haven't detected yet, the neutralino, for example, if that is not detected, then that's extraordinary evidence, and I think we start to need to think more carefully. But I don't believe that anything that's been put forward so far to support MOND is extraordinary evidence.
So, Benoit, we need extraordinary evidence, but we don't have that at the moment.
Well, I mean, I think it's not disputed, as we can hear, the fact that on galaxy scales, the predictions of MOND are working. Then the whole question is whether this success is an emergent success due to the existence of WIMPs and the feedback that you would get from the visible matter and the supernova explosions, etc., or whether this is a fundamental relation between distribution of visible matter and the gravitational field. My point of view is that because this relation works so well, and because it's history independent and environment independent, it works for galaxies that have had completely different histories and environments. And the fact that such a simple relation works observationally is, to me, extraordinary evidence that something fundamental is going on.
Karen?
I would perhaps bring up dwarf spheroidal galaxies, which I believe aren't fit well by the MOND paradigm. The fact that you need dark matter anyway on cluster scales. And, I agree, MOND as a sort of phenomenological description for rotation curves of galaxies works very well for all of the galaxies that are published in MOND papers. I don't think it works so well for absolutely every galaxy we've ever observed.
Well, I think most of the papers that have claimed to have found a big problem with the rotation curve in MOND have been shown afterward to be rather weak. There are, on galaxy scales, there are, in my opinion, no strong experimental observational contradictions to the MOND predictions. Karen was mentioning dwarf spheroidal galaxies. I'm not sure we know so well the distribution of dark matter in dwarf spheroidal galaxies. And then there is another thing about dwarf spheroidal galaxies, which is directly related to our work, which is that the spatial distribution around the Milky Way and around Andromeda is completely ununderstood. And what is really important, I think, about what we have found in this work is that this past collision between the Andromeda and the Milky Way could actually generate new galaxies. So the dwarf spheroidal galaxies could have been born in this encounter, and this would naturally account for their very special geometry.
Hongsheng.
So it's interesting. When we take this model backward, we found this collision. And in the beginning, I thought it was going to be a big problem because, there was no sign of anything happening in the Milky Way. So I was half to think that if MOND was a falsifiable theory, this is falsified because we do not see sign of a galaxy collided in the Milky Way. However, I was drawn to the attention of a few new observations. The satellites around the Milky Way are not arranged in some random fashion, but in one great circle, that is one disk that encompasses Magellanic Clouds and a few other smaller satellites. And this reminds me that this bad thing that I found about MOND may even be the solution to that.
So, Karen, do you think there's evidence for a collision between these two galaxies in the past?
No, not really, to be honest. I certainly agree that the distribution of satellites around the two galaxies is very interesting and something that warrants further study. But again, I don't think that it means we need to change the standard models of gravity on these scales. I mean, I think, again, this is potentially quite testable if you look very carefully at the ages of the satellite galaxies. I don't think you'll find that they all form together at a single time in a collision. And again, the sort of the physics of star formation, of how gas works, that's not something that you can run the clock backwards on. So that seems like an oversimplistic treatment of that. And also in the standard model of CDM, it does leave a lot of wiggle room, basically, for finding unexpected things on galactic scales. So I don't see any problems with that at all.
And I guess we have quite well-established theories of how galaxies interact when they collide.
Yeah, if this is indeed the model that we should expect, I'd like to see a proper simulation, including star formation in both the MOND and the dark matter paradigm, and I very much hope that that happens. And again, I think it's really important to explore lots of different ideas. I'm just not seeing any extraordinary evidence here that MOND is definitely the right answer.
Hongsheng.
The question is not really whether MOND is definitely the answer or not. Is presently there are observations out there of a vicinity, things we really know very well, we can see the structure, that we cannot find a good answer in the standard frame. Right now, we don't see any solution to the disk of satellite. This point has been made not just by me, but been made by many people. Whether you believe Mond or not, that's a different issue, but some interaction like this has to happen to create things.
Karen?
So just one statement, just that large numbers of satellite galaxies are very natural in the CDM paradigm, and that they naturally form in small sort of microhalos of dark matter. The distribution is slightly unusual, but galaxies have all sorts of different formation scenarios, and we know that star formation proceeds in different ways in different parts of the universe. So I suspect we're going to find an explanation for the unusual distribution of satellites quite naturally within cold dark matter to do with the formation history of the two galaxies, and don't need to go to the lengths of claiming all of these galaxies are tidal dwarfs.
Benoit?
So I think the whole problem here is that within the cold dark matter framework, this distribution of satellite galaxies and actually the number of dwarf satellite galaxies that we see around the Milky Way and around Andromeda are both problems that at the moment the community is trying to solve by just waving hands and not having a very concrete model being able to explain it. And these two problems are difficult to reconcile within the dark matter paradigm.
That was Benoit Fabi from the University of Strasbourg. And earlier we heard from Hongsheng Zhao of the University of St Andrews, and also from Karen Masters from the University of Portsmouth. Going right back to the earliest star charts, huge projects which collect data about very large numbers of objects have long been at the heart of astronomy. In recent years, the size of these projects have grown into vast international collaborations, working on projects which, in some cases, cost hundreds of millions of pounds. Some people have dubbed these projects mega-surveys, and I asked Professor Andy Lawrence from the University of Edinburgh what the term means.
Well, a survey is any systematic collection of data over a large piece of sky, and a mega-survey is just a very big survey. There are good reasons to pre-collect data, as opposed to letting each astronomer go and look at the piece of sky they want to, the individual object they want to. That kind of targeted science will still go on, but there's been a long tradition in astronomy of systematically surveying the sky, putting the data in an enormous database, and then letting astronomers get at the archive, the databases, to do their science.
So why are astronomers suddenly so interested in these very big data sets? Is it because we're tackling difficult problems that need very large amounts of data?
There certainly are examples. This happens repeatedly, but it's not new. There's always been big things. X-ray surveys, IRAS, recently WISE, the first mid-infrared survey. So there's been a long tradition. But there are some problems where you just need extremely large amounts of data. It can be because the thing you're studying is physically big on the sky, like making a map of the Milky Way, looking at its structure. Sometimes it's because you simply need extremely large numbers of objects. So the interesting modern example is weak lensing. It's trying to map out where the dark matter is by looking at distortions of galaxies caused by the light moving through the ripples of space-time caused by the dark matter. Any one galaxy, this distortion is a tiny effect. But if you look at lots and lots of galaxies and see if it's systematically in the same direction in one piece of sky, then you can figure out what's going on with the dark matter. And then to make a map of the dark matter and look at its structure, you need to repeat that in lots of positions on the sky. So to do that, you need millions and millions of galaxies. You need to beat down the noise to get an accurate measurement, and to see it at all, you just need lots and lots and lots of galaxies.
I guess one factor has been that we've only recently had the computers that can process these huge volumes of data.
That's true. And in fact, the ambition of surveys and the capability of our computers are always kind of leapfrogging each other. So I think that's always been true, but certainly at the moment, the new things we're contemplating need some pretty serious processing power. The big hope for lensing is the Euclid space mission, which should be launched hopefully about 2019. It'll make measurements of these distortions of galaxies from space, which will be very accurate, but processing the data to eke out the information is going to be very hard work. The new thing that's exciting people is looking at the sky repeatedly to see things that change. That's starting right now on a small scale, very bright things like SuperWASP, looking for exoplanet transits and so on. At a much deeper level, Pan-STARRS, which I'm working on, is very exciting, looking for supernovae, for quasars doing strange things. So you need to cover the sky repeatedly, and you're looking for very rare things. So you need to, for instance, to look at the sort of tidal disruption events that I'm looking for in the nuclei of galaxies. They're very rare. Happens in one galaxy out of every 100,000 or maybe a million per year. So you've got to look at millions of galaxies repeatedly because one of them will go bang. It's the classic needle in a haystack problem.
I guess this has been quite a big societal change in astronomy in that it takes a lot of telescope time to do these big surveys. So you have these very big collaborations of people working on them.
You do, and people often worry that astronomy is becoming more like particle physics. It's all being done by giant collaborations, and you have to do what the prof tells you, and so on. But for me, part of the joy of surveys is actually that although we do have big projects, and Planck was the classic example recently, with a survey you can recreate the sort of anarchic, individualistic approach that astronomers love. Because you get a professional team together to collect the data, make the database, make the query interface, and so on. And once you've done all that, then any smart postdoc can just get in there, have a smart idea, search through the data, find something new and interesting. So it doesn't mean that astronomy has to be done in kind of large, faceless, Stalinist teams, as it were, and we can keep our anarchic approach. So for me, that's very much a part of why surveys are important.
So we're seeing some very large projects at the moment, like the European Extremely Large Telescope and the Square Kilometre Array. But we also do see some smaller projects like SuperWASP, which I think was really built on a shoestring.
I think we're very likely to keep a mix of the big and small, but there is an inexorable pressure towards bigger things, just because we're always wanting to collect more and more data to look at fainter and fainter objects. On the other hand, there's always new ideas that are usually first explored with a relatively modest facility. So I think we'll have both, but there will be more and more big science.
Thanks, Andy. That was Professor Andy Lawrence from the University of Edinburgh. Several of the world's space agencies are now talking about sending missions to asteroids to learn about some of the solar system's smallest rocky bodies. But how structurally sound are their surfaces? Could it be that they're actually so weakly bound together that they would be quite unable to support the weight of a space probe? Ben Rositas from the Open University recently flew a simulated mock-up of an asteroid on board an aircraft to find out.
At the moment, several space agencies are planning several space missions to try and land on an asteroid and to grab a sample. But not a lot of work is being put into actually looking into how the surfaces will respond to when an actual spacecraft touches down and tries to interact with the surface. So we came up with this experiment.
So the problem here is that the gravitational field of these asteroids is quite weak, and that means that this material, I guess, is less strongly bound together than that of, say, the Earth.
Yeah, exactly. On the Earth, we see a lot of processes involving granular matter, as we call it, sand, and being driven a lot by gravity. But as asteroids are so much smaller than the Earth, they've practically got no gravity to hold this granular matter together. So it's intriguing to look into how these processes change when there is no gravity.
You've used the term avalanche for how this material might collapse. I guess it is a bit like snow in that it's not very well bound together.
These dry materials have some degree of strength, but once you push them beyond their limit, then all of a sudden something gives way, and then you get a granular flow, as we call it. Flowing as an avalanche is an extreme case of a granular flow. And spacecraft who've visited asteroids already have seen evidence of avalanches occurring on these surfaces. So it's clear that these processes do happen on asteroids as well.
Are there any other phenomena that you see when you disrupt the material on asteroids?
Yeah, definitely. One analogy I like to use is the umbrella at a beach. Imagine you want to try and get this umbrella to stand up at a nice sandy beach. The first method you could do is just try and stab it into the ground. But generally you find that the sand resists you. So the next way you could try is you could try turning the umbrella, and that helps a bit. But the best way to do it is you keep on alternating the direction. This is because you're breaking these force chains, as we call it, when you're continually changing the direction of the motion. So we tried to see if this process could work on an asteroid surface, and we found that this process does work. But we also found that usually on the Earth, it's the grains of sand closest to the pole that rotate around the pole the most. But when we try this on an asteroid surface, we find that essentially the rest of the beach would turn around with you if you try to land on it in a particular direction. Now you could, the transmission, the force being transmitted across to the other side of the asteroid and cause an avalanche on the other side. So it's really, really quite strange.
I gather you actually had the opportunity to fly your experiment on an Airbus A300. How did that come about?
Yeah, we flew our experiment on a parabolic flight, as we call it, about 4 years ago, and that came through a competition through the European Space Agency called Fly Your Thesis. Initially, there were 50 proposals put forward. 25 of them got shortlisted, and they selected the best 4 to go and fly on the parabolic flight in November 2009.
Did you basically fly a mock-up of an asteroid surface to see how it would behave in that low-gravity environment?
Not exactly, but an idealised piece of kit so we can modify the surface in a controlled way. So basically we have a rotating drum, and it's filled with 1 million glass beads, and we slowly rotate them and image them with high-speed cameras. And we'll see what happens to the grounding material by tracking the individual beads with a particle tracking algorithm afterwards.
How much do we know actually about the sizes of the particles that you would have on the surface of an asteroid?
They range in size from dust size, a few microns as we call it, all the way up to centimetre size, so pebbles, all the way up to metres and 10 metres size, so you get rocks and boulders. In particular, some asteroids, as we call them, are rubble piles, where they're basically made of small particles all the way up to boulders, all stuck together by just gravity.
Obviously, it's going to be very important to understand this before we try and make a controlled landing on the surface of an asteroid. When do you think there might be spacecraft landing on asteroids?
Well, there have already been 2 such landings on an asteroid. There was the Shoemaker mission, which was run by NASA. That was initially an orbiter mission for the asteroid Eros. And to the end of the mission, they decided to just land on the asteroid. And so they got it down, and the spacecraft sent back data for several days afterwards. We don't know what state the spacecraft was in afterwards. And then there was the Japanese Hayabusa mission to Itokawa, where they actually tried to grab a sample from the asteroid by hovering, but they didn't get the hovering quite right, so temporarily it touched the surface for a few moments before hopping off and returning to the Earth.
What's the next step for you? Are there going to be more spacecraft landing on asteroids that will collect data to help you constrain your models?
At the moment, the European Space Agency has the Rosetta mission going to a comet, and it's going to try and land on the comet late next year. And we'll all be watching with great interest to see how it'll cope. Because there are some theories that its surface could be a bit like talcum powder, and trying to land a spacecraft and get it to stay on the surface or not get buried on the surface when it lands is going to be an interesting challenge.
That was Ben Rositas from the Open University. That's all for today's Naked Astronomy, but don't forget you can find more episodes of the podcast at thenakedscientist.com/astronomy. If you'd like to get in touch, you can send a tweet at Naked Scientists or email astronomy@thenakedscientist.com. Naked Astronomy is produced by me, Dominic Ford, and comes to you from Cambridge University with support from the Royal Astronomical Society and the Science and Technology Facilities Council.